Good morning, everyone. I will soon start sharing the screen. Yeah, good morning. I hope all of you can see the screen. This is the last slide of the last class, where we finished proving that elementary number theoretic lemma. So today we will look at a result which uses that lemma, which will also be useful. Today itself you will see its use, and also later on in the proof of that main theorem. So suppose you have a irreducible aperiodic Markov chain on a state space S. And suppose P is the transition probability matrix of that Markov chain. Excuse me. Then the proposition says that for every pair of states, that is X and Y, in S, the state space, there is an integer n0 greater than or equal to 1, which could possibly depend on X and Y, such that P to the power n xy is strictly positive for every n greater than or equal to this n0. In this case, the x can also be equal to y. So this is the main this thing about aperiodicity, because we expect the GCD of that set, where for all n for which this happens, to be 1. So which basically is that there should be a lot of consecutive n's for which this is strictly positive. And in particular, this happens after a certain, eventually all of them are greater than 0 for a given X and Y. And in case the state space is a finite space, this n0, which here we said can possibly depend on X and Y, can be chosen independent of the states. So in such a case, there is an integer n0 greater than or equal to 1, such that P to the power n xy is strictly positive for all xy in S, for all n greater than n0. So once we prove the first assertion, the second assertion is trivial, because if S is a finite state space, the total number of pairs one can choose is, if the state space S has cardinality k, it will be k squared. So you choose the maximum of all those n zeros corresponding to each xy. That will still be finite. So essentially, basically, the proof is concerning the first assertion. Note it down. Okay, let's look at the proof. So choose an arbitrary A in the state space. Let I, capital I, denote the set of all n greater than or equal to 1, such that P super n AA is strictly positive. So since it is an aperiodic chain, the GCD of this set I is 1. And also, if M and N belong to this set capital I, then it is easily seen that M plus N also belongs to capital I. So now apply the previous lemma. So by the lemma, there is an integer n sub 1 greater than or equal to 1 such that P super n AA is greater than 0 for all n greater than or equal to n1. I leave it to you to convince yourself that this happens by the previous lemma. You apply previous lemma to the set I, capital I. Note it down, please. Okay. So now choose, you have the earlier thing you did for some particular A. Now you pick any pair XY. Since the Markov chain is assumed to be irreducible, X and Y communicate. Rather, X and Y communicate through A in the sense that X to A to Y is possible. So there are integers n sub 2 and n sub 3 greater than or equal to 1 such that P super n2 XA is strictly positive and P super n3 AY is strictly positive. Then for any n greater than n1, remember that n1 was chosen just with A in hand. Then P super n2 plus n3 xy is greater than this, the product of greater than or equal to the product of these three guys, each of which is strictly positive. So this happens for every n greater than n1. So for this pair xy, you can take n0 xy as n1 plus n2 plus n3. Then you have this. So this proves the first assertion of the proposition. Please note it down if you want. Okay. So as I had mentioned earlier, if the state space is a finite set, then the second assertion is easily follows from the first one. Right. Yes. Because the number of such pairs is itself is finite. Take the maximum of all those guys. Yeah. Okay. Now, using this, we see what happens in the case of a finite state space. It gives you quite a bit of information. So let Xn be a irreducible aperiodic Markov chain on a finite state space, yes. And the transition probability matrix, let us say it is P. So by the earlier theorem, whose proof we have not yet given, we know that there is a limiting probability distribution, pi. So this pi will also be the unique stationary probability distribution for the Markov chain. So since it is the limiting probability distribution, we already know that P super n xy converges to pi y for every x. The thing doesn't depend on x. And that happens for every state y in the state space. The additional information here we get is concerning the rate of convergence. So then there exists real numbers, positive real numbers A, and also a number alpha between 0 and 1, such that this happens. Of course, here alpha can even be 0. It doesn't matter. The important thing is, of course, alpha is non-negative and it is strictly less than 1. Among these two sort of constants here, this A and L doesn't depend on N, of course, nor do they depend on X and Y. The alpha is the more important parameter or constant. That is the one which determines the rate. So since alpha is strictly less than 1, alpha to the power n goes to 0. And so this is a kind of geometric rate. So the above bound is called geometric bound for the rate of convergence. And in that case, the rate is alpha. A is some sort of multiplicative constant. It doesn't matter if A is bigger than 1. I wanted to make another comment. Some authors also call this kind of a convergence exponential convergence, because alpha can be written as e to the power minus of mod log alpha. Since alpha is less than 1, the logarithm will be negative. So that is it. Later on I decided not to write that, but then I forgot to erase that. So this kind of convergence is also called exponential convergence in some books. Note it down if you want to. This proof is also sort of constructive in the sense that it tells you what can be alpha. So the rate of convergence, etc., can be important, especially you want things to be converging quickly, fast. And especially if the state space, though that may be finite, but if the number of elements in S is huge, then these things do matter a lot. Okay, let's look at the proof. See, we already know that pi sub y is strictly positive for all y. Because in this case, remember that we have a result earlier that all the states will be positive recurrent. And since S is finite, by the earlier that proposition which we proved just now, there is an n0 greater than or equal to 1 such that P super n0 xy is strictly positive for all x and y. So this is strictly positive for every x and y, and this is a finite state space. So take the minimum of this minimum with x and y running over the state space. Denote this by delta. So clearly this is strictly positive because S is finite. Now we will define m sub small n and small m sub n and capital M sub n for each n. So put m0 of y equal to 0 and capital M0 of y equal to 1. That is when n is equal to 0. And for any n greater than or equal to 1, small n sub n y is minimum of all these entries. That is, you take the p power n and take the minimum of all the entries in p power n. That is small mn, and capital Mn is the maximum. Of course, obviously, small m sub n is less than or equal to capital M sub n. But we claim something more. Small m sub n is less than or equal to small m sub n plus 1, which of course less than or equal to capital M sub n plus 1, and which is less than or equal to capital N sub. In other words, small m sub n is an increasing sequence, whereas capital M sub n is a decreasing sequence. And both the sequences are in the interval 0 to 1. These are all basically probabilities. So they lie between 0 and 1. So once we prove this, immediately you see, because of our this thing, say small m sub n0 would be less than or equal to small m sub n for any n greater than or equal to n0. So all these guys would be greater than or equal to delta for n greater than or equal to n0. Anyway, that we will be using later. So that's one of the implications I just want to point out at this stage itself, which we will be using it, and it will also you will mention later. Okay, note it down. So we prove that claim. As mentioned earlier, the middle inequality is trivial. Okay. So we want to prove this part. And the proof of this will be sort of similar. So note that P super n plus 1 xy, which is by definition summation over z, P xz, P super n zy, and this is greater than or equal to, you can, each of this term would be bigger than or equal to P to the power n uy, u running over the state space. So that can be pulled out, and what remains is in this summation over z, P sub xz, and P is a stochastic matrix. So this sum is equal to 1. So you have this. So now if you take minimum over x on both sides, then you get small m sub n of y is less than or equal to small m sub n plus 1 of y for all n and y. So proceed in a similar fashion with, of course, instead of taking the minimum, take the maximum, etc., etc. So then you get the other, this inequality. So the claim follows. You may note it down. Excuse me. Okay. So for each y, small m sub n is a non-decreasing sequence, that is basically increasing sequence, and capital M sub n is non-increasing sequence. And these things are bounded sequences, of course, bounded by 0 and 1. Consequently, the limit exists. Oh, these unnecessary braces are there. Remove. Some copying and pasting I would have done, and I would have forgotten. And of course, what the limit is very clear. We already know that P super n xy as n goes to infinity goes to pi y. And you know that P super n xy is sandwiched between little m ny and capital M sub ny. So both these sequences, little m sub n and capital M sub n, converge to the same limit, namely pi y for every y. Note it down if you want. Okay. So in fact, little m sub n increases to pi y, capital M sub n decreases to pi for each y. So since P super n xy and pi y both lie between these two for each n and for each xy, so we have this inequality. That's very obvious. So then the approach we are going to take, I mean, because of this asterisk, is clear. We will try to give this a bound for capital M sub n minus M sub n, little m sub n. So as I had mentioned, verify that this, of course, delta is strictly positive for all n greater than or equal to n0. Small m sub n y is greater than or equal to delta. I mean, this is the basic verification you have to do. The other things are automatic. So convince yourself that this happens for all n greater than or equal to n. Because this one, little m sub n will be greater than or equal to little m sub n0 by the claim. So this n0 we have got basically using the previous proposition. Namely, we have an irreducible aperiodic Markov chain on a finite state space. So the number theoretic lemma basically helped us in getting this. note it down if you want. Okay. Now there will be some manipulations. So because see the P super S, see S can be any integer. ZU, this is it's a probability. So between 0 and 1, excuse me. So P super N0 XZ. So that is greater than 0. That we know. Because of aperiodicity, for any X and Z, this is strictly bigger than 0. As a matter of fact, these things are bigger than or equal to delta. And this is dominated by 1. So at most, or rather at worst, this will be minus delta. So this is greater than or equal to 0 for all S and all X, Z, U and V. See these indices, or rather this are indexes are can possibly be different from each other. All those subscripts can in principle be different, distinct rather. Consequently, so now there is a sort of certain manipulations, you sort of keep track of it. So what we are going to do is, we are going to go in terms of steps of N0. So P super K plus 1 times N0 sub xy. So that we can write as the product of P super N0 and P super K times N0. So that is what we have done here. Summation over Z, P super N0 xz and product P super K N0 zy. So now we have brought this here and taken this inside. So P super K N0 zy product P super N0 xz, and from that we subtract delta times P to the super K N0 yz. And this observation ensures that these are all strictly positive. I mean, not strictly, greater than or equal to 0. So in this process, what we have done is we have subtracted summation over Z P zy Kn0 times delta times P super Kn0 yz. So to restore parity, we add that. Now, here we take minimum of this as Z varies over S. And take that out of the summation. So greater than or equal to minimum over Z P super kn0 zy, and then we are left with this. And here, this is summation over z, but this also we can write as Pyz zy. And if you view it that way, just precisely it's P sub yy of P super 2k times n0 yy. And here, since P super n0 and P super kn0 both are stochastic matrices, we have this summation is precisely 1 minus delta. I mean, each of the summation will be 1. So what you have is 1 minus delta.
Sir.
Yes.
Your voice is again has become so low.
Okay. Can you clear here now?
Yeah, now it is clear. Now it's clear.
Anyway, you can make out all these things, right? There is some manipulations here. So which is not, it may not look canonical if you look at it for the first time. So here we are taking this thing out, and we are basically adding the subtracting and adding this guys. Oh, there is a small typo. This is capital P super 2kn0 yy. Please check it. And also note that this minimum over z of P super kn0 zy is precisely, by definition, little m sub kn0 at y. Note it down. So this is a crucial step in this proof. Note it down. All right. So now take minimum over x in this. This side is independent of x. So when you do that, what you get is little m sub k plus 1 times n0 at y is greater than or equal to 1 minus delta times little m sub kn0 y plus this delta times p super 2kn0 yy. The next step is clear. Do kind of very similar this thing with instead of playing with the minimum, maximum. So now you subtract single dagger from double dagger. Or rather, it may call two daggers or whatever. Double dagger is the other one, no? Where with a straight line and then two horizontal. Anyway. So you subtract this one from this. Then these two get away, cancel each other. So then what we have is capital M sub mk plus 1 n0 y minus small m sub k plus 1 times n0 y is less than or equal to 1 minus delta times the similar thing with k n0. Please note it down if you want. So the next step is clear. You iterate this. You have this is dominated by 1 minus delta times the similar thing with instead of k minus 1 and so on till you get to k equal to 0. Then m super 0 y you remember is 1 and little m sub 0 of y was 0. So the final this thing would be 1. Please note it down. So if you iterate, then you get this happens for k equal to 1, 2, 3, etc. So by star you remember was not star, asterisk. Star is different in a tech maker, this thing I'm using. This is our asterisk. So by that, and what we have above, we have mod p super k n0 xy minus pi y is less than or equal to 1 minus delta to the power k for k equal to 1, 2, etc. and for every x and y in the state space. This is double dagger. So if this n sub 0 happens to be equal to 1, in that case, our proposition, our theorem is completely proved. If that n sub 0 is actually equal to 1, the required conclusion is precisely this, with capital A equal to 1 and alpha equal to 1 minus delta. This is strictly less than 1. Note it down if you want to. So suppose n0 is greater than or equal to 2. So then any integer, any positive integer n, you can write as something mod n0. So that means you can write n as k times n0 plus r. So k is really capital N divided by n0, the integer part. And this is the remainder. So in this case, p super k n0 plus r sub xy minus pi y mod of that. So we write this in terms of summation over z p super r xz and p super k n0 zy. And here also like that. And now this is summation over z. This sum is basically 1 because p to the power r is a stochastic matrix. So convince yourself that this equality is correct. We are using the fact that p super r is a stochastic matrix. So that is obviously less than or equal to this. And by this double star, this is of the form p super kn0 zy minus pi y. This, for this, we already have the estimate from here. That is 1 minus delta to the power k times this. But then p super r is a stochastic matrix. So this is equal to 1. So you have this. So in particular here, p super n xy minus pi y, you are getting it less than or equal to 1 minus delta to the power the integer part of n divided by n0. This k is precisely n divided by n0, the integer part. So we write this as, this is precisely this one. And then we multiply and divide by this expression. And these two together, the first two objects here together gives alpha power n, where alpha is 1 minus delta, the whole thing raised to power 1 over n0. If n0 is not equal to 1. If n0 equal to 1, it reduces the previous case. And this guy, you bound it by, it turns out to be this. So that completes the proof of the theorem. So if you, of course, this is the thing for today. You want me to go back to any of the slides? Yeah, if nobody has anything, any comments or questions, I'll stop sharing and end the session. Okay. So we will meet again on Friday.
So is today's class over?
Today's class is over.
Okay. Okay. Okay.
So maybe I should also mention every time, here ends the class. Okay, good.